we started with visual document understanding. At that time, even GPT-3 handles around 2K, 8K window contexts, then it was not working. But later, after we get the result from Donut, the ChatGPT gets better and it handles more window context. Then we tried that, so we get a good result from the ChatGPT. So as you said, ChatGPT 4 has a capability of taking images and generating results based on your prompt. That's also something that we could integrate into the research as a future work. But even if you look at table of content, it will not be a single page, right? It will have some continuity. Like it will not only present it on a single page. So in that case, what you have to have is some model that seriously understand the sequences of the table of content, or you use text. So if it is text, you will have all the window or all the table of content in a single text, and then you can extract from that. So this can also be applied for that case. Yeah, thank you.
A question I would raise is, I mean, the main application of your work, in my opinion, would be for the structuring of documents that are primarily composed of images, either a scanned document or something similar. And however, in your presentation as well as in the document, there is some mix-up between a document that is an image and the document that is presented in a textual format. So in your opinion, the main contribution when we look at the results that you have presented, is it due to the OCR, or is it due to the work that you did on the structuring that we see in the results?
The question is, I didn't understand the question a little bit.
To say, I mean, if all of the documents that you have worked on were scanned documents or images, then it would be clear to say, okay, is it the OCR that's performing well, or is it the document structuring, the GPT that you have used that's working?
Okay. Yeah. Thank you. Now it's clear. So both, like it is not OCR actually. It is OCR theory, but it is visual document understanding. Donut is visual document understanding, and it works. You give it an image, then it generates a JSON format. Like when you fine-tune your model, you give it an image. The label is a JSON format. So it will also give you structured output in a JSON format. The same with ChatGPT. So we have both in text and in image. The data both exist in a text and in image. So both modalities are available. If it's clear.
Yeah. Thank you, Dagaga. Okay, so the next presenter, if is or she is available, it is Girma Andualam, Samuel Adeno, Gabriel Xavier, Gabriel Libanos. Okay, so so in the meantime, while we wait for the three presenters, we have listened to two interesting research works on developing bidirectional English Anuak machine translation using deep learning approach and automating table of content structuring, leveraging GPT 3.5 and Donut for efficient document indexing. We will have a tea break at 3:20. We have 10 minutes. In the meantime, you can network and discuss while we solve the issue of the presenters. Thank you very much. Yes, we can hear you.
And it makes it vital for means of communication, and AI solution with this language can ease so many things. So there are some people's, as you can see in the screenshot below, around 48% of the adult population are have difficulties in writing and reading. So that can be like a big audience for us. So developing this solution can help these 48% of the Amharic speakers, especially, then the rest of modern solutions like Siri and the others will come after that. So it is inclusiveness. So this AI solution will be inclusive for those who are in need of such kind of technologies. So what are the existing models? To our research, we only took an example of those who are those that are publicly available. So in this case, we selected out 2 speech recognition models, and both of them, as like the modern solution is fine-tuning the speech recognition models, or models which are trained with audio data. The 2 models here we selected out are the fine-tuned version of wave-to-wake model of Facebook. And I will explain a bit about what the wave-to-wake model of Facebook is. And as you can see, there is small or kind of remarkable result which is recorded by those models. There is a word error rate of 24.92 by speech brain, and here the other model has 26% of word error rate, which means word error rates in this point, like to explain for those who don't understand, is the what percentage of the words are incorrectly recognized. So this error rate is like the lower the error rate, the higher the accuracy. That's how we are measuring throughout this paper, so bear it in mind. So what are the challenges in the current ASR models? The current ASR models have mainly, the main issue is accuracy and semantics. Accuracy means the accuracy of those models in extracting those patterns is very low, meaning like there are some character misses or subword misses, and some information with that miss will be lost. So improving the accuracy will be the first point. Then the second one is semantics. Since the argulative nature of Amharic, the way we extract those subwords is through not with the word. It's more of like by selecting characters or by recognizing patterns from characters from the speech. So this way, when we organize the sentence, it may have a semantic issue because of like the spacing or some kind of things. And the second one is data quality. The training data that we have been using was like very bad, meaning like there are some human errors made by when collecting the data. And the third one is resource constraint, meaning the resource we have, like the GPU and the training data, is limited. So those factors has been contributing to the not developed models that we have so far. And the last one is dialectical variation. Even in Amharic, there are different dialects. So there is dialects in Gojam, Gondar, or Wollo, and other parts of Ethiopia. For example, like those who are not native Amharic speaker may have a bit of different dialects. So those 4 points were the main issue in extracting Amharic patterns to text. So our approach is has split the problem into 2 parts. The first one is how could we extract the patterns? So like if we improve the way we extract the pattern, that will give us a good character recognition. The second part is after recognizing those Amharic character sequences, we can use another method to correct those Amharic character sequences. So as you can see in the image, there is the first line shows an Amharic output or speech recognition output, which has like improper spacing and some character misses. So which is the main issues, so that we added another component, which is sequence to sequence sentence correction model, which corrects the output of speech recognition model to something which has a meaningful sentence. So we have a speech recognition model which extracts some patterns of the audio, and we have a sentence correction model which takes in the output of speech recognition and give out a semantically correct Amharic sentence. To depict the image, here we have the component diagram. The one below, like the waveform, shows the audio, and we have the audio extracting model, the ASR model, and the ASR model emits a character sequence, and the one you are looking at in the middle is the character sequence that is emitted from the speech recognition model. It has a character misses, and it has improper spacing, so that leads to something meaningless. So what we did was we added this one, the sentence correction model. It is a transformer model. It has encoder and decoder, and it is capable of taking the character sequence and emitting the correct Amharic sequence. It is trained to do things only, and the training process was like based on that, based on like a data which mimics the output of our SR model. The data availability is like very difficult issue, because the only data we had when training this model was only 10,000 speech sample with the corresponding transcription. So in this case, we used the alpha publicly available data set, and this data set had some errors, such as like labeling error, or the so-called human errors, or background noise, like this, or background noise. Like the background noise was by adding 2 or 3 sample audios of the training data and adding those 2 or 3 audio samples as a background noise for the other training sample, so that like we replicated the training data and we added around 14,000 additional training data points by this data augmentation process only. And the second data augmentation process was made to the training text corpus, or I mean the text data. So to train the sequence-to-sequence sentence correction model, we had to programmatically create an error into the training, the Amharic sentences, so that we will use that faulted Amharic sentences as an input for our sequence-to-sequence model to learn how to correct such kind of erroneous sentences, like that's made specifically to mimic the output of our speech recognition model. And there are some data preparation process that we took, for example, like normalization, extracting some symbols or unnecessary characters. And the normalization is, as you may know, Amharic has like some characters which has the same sound but different structure. So we normalized those kind of characters and created like selected out characters that are frequently used, and that will be used as the output of the final output of our speech recognition model, because we cannot use like the for example, in this case, if you can see it, there is ha, hamaruha, or ha, the fourth order ha. And so we selected out this, the ha or the first ha character of Amharic alphabet. This way we normalize the data set. There is also additional normalization that we used to lower the number of outputs of our model. We had to select out the vowel and the consonants of the Amharic language or characters. So in that sense, like, we selected out the base consonants or the 6 order characters of each character group. For example, for la group, la, lu, li, something like that, we selected the 6 order character, which is le, and we selected additional vowel groups of the Amharic sentence or the Amharic alphabet, which are like a, u, i, a, e, o, like the a, e, I, o, u of English. That way, we converted every character in our training data for the speech recognition model to something which is the combination of our consonant and vowel. That is specifically made to lower the number of output of our speech recognition model, so that it can boost the accuracy. In this experiment, we have done for like specifically for each character, and which will give us around 233 characters, and the phoneme level, which has only 37 character outputs. The model we used is like the first one was a fine-tuning process. So we trained on 53 languages. So we fine-tuned that model to give out the phoneme level and character level Amharic speech recognition models that we are presenting today. And the second one was like a simple transformer model, but with different vocabulary size and different is like we selected out 15,000 frequently used tokens in Amharic sentences. Then we use those tokens as an input and output for our transformer model. And there is also one model that we used, which is uses the 233 Amharic characters as an input and output. That way, like we used we developed our second model to take in and spit out Amharic characters in a way that corrects the the speech recognition model output. I think I should, okay, our speech recognition model has like a character level ASR, which is a short name for Amharic automatic speech recognition, and the character level ASR has around 233 unique Amharic characters. So the phoneme level ASR spits out only 37 character classification, for example, like the vowels of Amharic and the consonants of Amharic. Then after finding the vowel consonant combination, we convert the vowel consonant combination into Amharic characters. So there are two ASR models that we developed in this process. The sequence to sequence sentence correction model has like 3 components or 3 replicas. Sequence to sequence 233, which uses which has like 233 input and 233 output as like input and output token size. The sequence to sequence T5 and sequence to sequence BT5 has a token size or input and output size, but the only difference they have is the internal layers they consisted, and 3 of the models are transformer based encoder decoder architectures. The training procedure, the audio samples are also the validation results. I think the slide is not updated. Can you? Sorry, can you hear me? Hello? Hello? Yes? Yes? Okay, okay. Okay, the challenges we had when developing those models was like the data questioning, the complexity, the challenge lie in acquiring the label training data, audio data that was accurately, that training data accurately reflects the real world condition. Like the training data did not have like a background noise or some other noise that we expect from a real life noise, so it may not perform well in a situation where there is a background noise. The challenge was a resource constraint, so the computational costs like a GPU cost and other things were expensive. The other one was like that limited data we have could not give us a good accuracy. So not having the training data is also a resource constraint. Finally, the results after applying sentence correction to the existing benchmark models and our models, or before and after applying the sentence correction, gives like a remarkable or a big difference in the accuracy. For example, let's start from the qualitative results. Before correction, as you can see, the first sentence had like improper spacings, and for some cases there are like some missing characters. So that was the correction. As you can see, the Amharic sentence or the Amharic output was like significantly improved. So for those who don't understand the Amharic, you can see the result or the meaning here, and the one above has like some improper spacing. So if we were to translate the result into English, we may have like difficulties or issues. So as I presented before, the speech recognition accuracy of an existing model is the first issue is it is measured on a semantically incorrect testing dataset. The second one is it is not emitting out a semantically correct Amharic output or Amharic sentences. So the speech brain ASR model, after applying the 233 sequence to sequence sentence correction model, it is showing 7.4% accuracy of character error rate, which means out of 100, it misses the 7 characters, or it has like the 7 characters are or like altered or changed, and 28% of word error rate, which means like out of 100, 28 words are like incorrect. And to come to the last result, just as the results are obvious for you to compare, the last result or the best result is recorded by our phoneme-based speech recognition model, which is phoneme A wave to wake, and our the bigger variety of our sequence to sequence BT5 model, and it gave us around 5.5% character error rate, which is lower than the 7.4 character error rate of speech brain, and 23.3% of word error rate. And this result is on semantically corrected testing dataset of Amharic. So this 23.3% of accuracy is an improvement in both accuracy and semantic, which means like if you try to read this, the output of this model, it will give you something meaningful compared to the other models that we have publicly, at least. So for conclusion, our model has 5.3 with like we also measured the accuracy of an existing publicly available model on a semantically correct testing dataset, and their accuracy or the accuracy of that model was around 14% of character error rate, which is a big error to have. So our model achieved an 8.49% accuracy improvement, which is like a big improvement. And the benefits demonstrated the efficacy of integrating a pre-trained sequence-to-sequence model for sentence correction and enhanced handling of out-of-vocabulary words, like since we are using a subword level speech recognition, or speech recognition, the way we corrected this Amharic sentence outputs of the ASR model, is resolving the issues that are created by somewhat approach of speech recognition models. So the last one is we generated a semantically correct output, improving the overall model performance. So we adopted a modular structure, which are like a sentence correction model and speech recognition model. So this speech recognition model can be used with different languages. For example, we currently are training a model for Tigrinya and Tigra. So like we have developed another speech recognition that is yet to be released, and we have like a 9 with this language too. So this two component or like modular structure of the models can give us like the freedom to include other models like other language like Tigrinya and Tigra of Eritrea. For future work, like we are also like training, as I said, a sequence-to-sequence model for Tigrinya and Tigra, so that like the sentence, the character outputs of our speech recognition model can be used by a sequence-to-sequence model that is trained on semantically correct Tigrinya sentence or semantically correct Tigra sentence. So this model will give us the freedom to include other languages that are using the Ethiopic script. And the other future work that we have in mind is like including punctuation and other things that can properly explain the emotion or the real sentiment of the sentence. Thank you for your time.
Samuel, can you hear me?
Yes, yes, I can.
Okay, thank you. You took a bit more time than allotted, but anyways, so now it's time for question and answers, so discussion.
Okay, thank you very much for your presentation. On one of your slides, you have shown us you used your semantic correction on already existing model, and I would like to know on which of this existing model you have added this semantic correction layer, and which techniques does this semantic correction model used in order to come up with those corrected text outputs. And the other questions that I have is, how can you rate your automatic speech recognition model with existing models in order to assist the studies that require output of automatic speech recognition, such as spoken language understanding, when you see it with already existing models? Thank you.
Samuel, you may reply.
Okay. I think it is 3 questions that you asked. So the model I applied the sequence correction or the sentence correction on was the model from Speech Brain. So they had around 26 or 25% word error rate, which is measured on semantically incorrect testing data sets. So the result of that model, when applied directly into our semantically correct testing data set, was around 14% character error rate and 90 something percent of word error rate, which means like the spacing they added, or the spacing it was emitting was like significantly high, which gave it a very low word error rates on semantically correct testing data set. So the model is a speech brain, and after correction it gave us around our best model, it gave us around 24.9% of word error rate and 5.9% of character error rate. And our model, our sequence-to-sequence sentence correction model, has showed a big improvement on that model. The second question was like, which technique is used, I think, right? So the technique we use is, as I explained on the figures of the first 3 slides, I think, is transformer-based encoder-decoder architecture. And the difference we have in our models is like the token size and the number of layers of like our say sequence-to-sequence sentence correction model. And like those 3 models are built with encoder-decoder transformer-based architecture. And the third question, if I understand it properly, is how can you rate your approach on other languages? Is that so? Let me just answer it as I understand it. It's as far as, for example, for our model, it is best suited for Ethiopic languages. For example, Tigrinya, Tigre, and we are trying to collect data for Aga or Amni. And there is one language that we are targeting in Eritrea, which is Bilan. So far we are able to get data and see the improvement that our approach has on Tigrinya and Tigre, which will, the paper will be released soon, and it can be applied with the other languages like Auni and Bilan. So that way we found it to be like good compared to the other approach.
Any other questions? So if you answered the previous question, you stated that when you use already existing methodology, the word error rate was 99 or some 96% when you use the correct. And I mean, in my opinion, such an error rate, a word error rate is very high. And in different literatures and different researches, many people have done on Amharic speech recognition, and your claim, as I understand, the fact that they are not using corrected data with regards to word boundaries has inflated their result. So is your claim in your research specific to one research that has been done, or is this a claim on all or most of them?
Okay, our experiments took the publicly available model of speech brain. Like, we couldn't have a model, a publicly available model that can be used to show how good our result is. So we only selected the publicly available model. That's why it's like a single model that we compared to.
Have you tried to look into other?
And there are some approaches that sorry.
Have you looked into other data sets and other researches that have been done on encoder decoder transformer architectures, and they have used 32,000 hours of Amharic speech, and they have reported around 30% word error rate. And in my opinion, the result that you stated in table 2 of your document, that shows that their word error rate of 99.9% should be relooked to make sure that it's not maybe some problem with the data sets that you are using, or the methodologies that you are using.
Here the data sets we tested our result on was a corrected data set, semantically corrected data set of the one they used. So the accuracy they have, or they mentioned, which is 24.5, I think, is like correct on the semantically incorrect test data set. But when it comes to applying that model into the semantically corrected testing data sets of ours, it's generated such a big accuracy result. Character error rate of those models is around 14%. Even our model has like at the very beginning low error rates in like generating accuracy results. So like explain in terms of which data set I am mentioning, because like the data set was completely different, and I don't know how to explain. And to the point that you said, there are some papers that said we have around 30% error rate. Yeah, we have mentioned some papers in our literature review or related work section that reported such results, but it is not publicly available. So we cannot test that model unless we get the model, or like the model publicly. So our results here are based on the publicly available models that we have found during our experiment.
Thank you. Any other questions?
Okay, thank you.
Okay, thank you, Samuel, for the presentation and for the discussions that we had. Thank you very much.
Thank you.
So next, we have a pre-recorded video that's going to be. Okay, thank you. So next, we will have a pre-recorded presentation by one of the authors of the paper. The author is already has joined us, but to avoid internet connection issues and interruptions, we will play the video, and then after that, we will have a discussion session with the author. So the paper is Deep Learning Based Automatic Amharic-English Code Switching Detection by Girmao Andualam. We may proceed. Thank you.
Hello? Hello, hello?
Hello, Gurmao, you may continue, we can hear you.
Okay, okay. Shall I share? Hello? Hello? Okay.
We can hear you, you can continue.
Okay, thank you. So our research paper is deep learning based automatic Amharic-English code suite detection. So this is
Gurmao, apologies
yeah.
that we are not, oh, your slide is not visible. We are having a technical, okay, now you can continue. Please proceed.
Okay, okay. So can you pass the next page? So this is our research presentation of lines, the background of the study, the fundamental problems, and objectives of the study. Here we have mentioned is general objective and specific objective. And the other one is significance of the study and research design and approach. Then we will discuss also research result and discussion. Finally, we will discuss on conclusion parts.
Gurma, you may continue.
Yeah. Is it visible? Next
It's
page.
visible, you can continue.
Okay. So natural language processing is a subset of artificial intelligence that focuses on leveraging of natural language to bridging communication gap between human and a computer. So this NLP is the intersection between a computational linguistics, artificial intelligence, and computer science. So this is technology, popular technology to enabling its communication between a natural language like Amharic and intelligent computer. So Amharic language is one of its natural language processing, which have unique characters, words, phrases, as well as its structure and dialects, but from different foreign languages such as in Arabic, France, English, German, Portugal, and Turkish. These loanwords cannot translate with target Amharic language. But this research work is observing the tendency of code switch Amharic with English language, especially in social media platforms. So this code switch is linguistic terms. These linguistic terms that two or more languages variety or conversation with text style or speech styles. So this pursuit is a mixing of words, phrases, or sentences from distinct grammatically systems across sentence boundary with the same speech event or text. This event is occur whether is intentional or unintentionally, especially in word levels and phrase levels and so as sentence levels in social media platforms. They basically this linguistic or code switches, they have four types code switches. The one is tag switch, that is in terms of phrase. The intra-word switch, is occur in terms of word. The intrasentential code switch is occur in terms of sentence. then when you're written or when you're speaking in compound sentence, so one sentence is Amharic, one sentence with another sentence, which means English sentence. At the time, this type of code switch is intra-sentential code switch. And the last one is intersentential code switch. Those is basic types of this code switch. So when it comes to this statement of problem, as far as this research, shall I pass the next page? Statement of problem. Hello?
Yes, we can
Hello?
hear you. Please proceed. We can hear you.
Then as far as this, as far as the researchers has now, no study has been done on detection of Amharic-English code switch, whether it is machine learning or deep learning. So in social media, is happening with the tendency of code switch with Amharic with English. So at this time, they happen or they occur in social media resources with misunderstanding or misinterpreting of information. And the other one is happen to region of language. There is, when you say this linguistic expert, there is pursuit is dirty communications. And the last one is when it comes to this technically, there is pursuit is the challenge of these Amharic-NLP tasks and cybersecurity tasks when building with NLP-based cybersecurity tasks. So for the existing in American natural language processing task for papers has a limited. That means capability of handling or code switch. For instance, the code switch, such like the, I mentioned this, is deliberately from this sentence, there is they're mixing with two languages. That means American English. This time there is challenge of this when machine translations, hate speech or sentiment analysis, and NLP tasks there is the challenge of this code switch. So when it comes to this, the general objective of this study, the main objective is they develop the model automatical Amharic-English code switch detection using deep learning approach. Hello?
We can hear you. Please proceed.
Okay. So the main objective is also to develop the model of automatic Amharic-English code switch detection using a deep learning approach. So in order to accomplish this, initially Facebook and Twitter comments and posts from scratch. Then the second one to annotating the code switch expert annotated by expert, which means by linguistic experts, and also to pre-processing Amharic-English code switch dataset. And the next one is adopted or applying of these Amharic-English, deep learning algorithms. We have a comparison of different deep learning algorithms, and to detect a testing of this English code switch detection. And the last specific objective is to evaluating the model performance Amharic-English code switch detections. We have evaluating the model with different models. So after addressing of the problem, this research gives some significance. The next page. So the main significance of this paper would be to prevent the language from being regions. That means to transmitting this distorting Amharic language to the next generations. And also would be reducing misunderstanding and misinterpretation in social media users. And the other significance of this research is reducing the challenge of this Amharic language. The NLP tasks of this, such as the hate speech detection, language identification, Amharic machine translation, post-up, and blah blah. And the last one is to the significance of this paper is improve the function or the meaning of the language can be separated. So after addressing the problem, this research is addressing those problems. So when it comes to this research design and approach to investigate the Amharic-English code search detection on social media platforms, we conducted with data science, where you have designed, developed, and also evaluating and articulating and addressing the solutions. So this is a proper system architecture. The first one is here is the Amharic-English code search data set. After loading this data set, we will to text pre-processing. The next is such like is normalizing, then cleaning unwanted characters or any bad issue. And the other one is to text morphological features, especially is English post tagging you have used. And other after this post tagging to pass this tag sequence splitting and sequence padding for ecologies. Then after this tag sequencing, then we have data splitting. We have splitting our data set is training and testing. After splitting this data set, testing and training data set, there must be training data set, there must be word embedding. After this word embedding, we have building the or adopted these deep learning algorithms. Then such like is CNN, BLSTM, ByJerry, and we have used also one hybrid algorithms that means CNN with ByJerry. Then after adopted this model, this saving this model. Then after saving the model, hello?
Please continue. We can hear you.
Okay. Yeah. After saving the model is code switch. The sentence is code switch or not. If the sentence is a standard sentence, that means the sentence or the text is Amharic, there is normal, there is non-code switch. If the sentence or the text is code switch, then what type of code switch here? This intra-word, tag switch, or intra-sentential code switch? Based on this is our proposed system architecture. So this is suggested structure system comprising these several stages. Initially there is text processing, there is data cleaning, normalization, tokenization, abbreviation expansion, and English post tagging, as well as is nonsense, that means non-meaning words also is pre-processing or removing. Then they subsequently after this pre-processing, they must be passed to this the other adaptation of parts. That means for adaptation of these deep learning algorithms, such like CNN, ByLSTM, ByJarry, and there is combination of CNN with ByLSTM. This is our text processing phase. Based on this, we are processing this our Amharic-English code switch detection. Okay, the other ones. Next page. Next. Hello. Hello.
Yes.
I mean, word embedding. Back to one page. Back on page. Yeah. So we have used word embedding from here. Normally, this every sentence. So I mean, every sentence there must be representing vector representations. So we have used default word embedding, that the embedding layers for these proposed systems. And after this representing sequence, the dense vector representation is and output as input deep learning algorithms, either CNN, ByLSTM, ByJarry, or combination of CNN with ByJarry. So next page. The other one is deep learning model in the future. Can you pass? Hello?
Can you tell us which slide numbers that you are referring to?
Slide 11.
Slide 11, please.
11. Yeah. The other one is deep learning model and feature extractions. So it's investigating the performance of
Grimau.
approach for Amharic-English
Grimau,
detection. Yeah.
you have 5 minutes, okay?
Yes. Okay. So we have evaluating these 3 single algorithm, deep learning algorithm, and 1 hybrid algorithms, which means CNN, PLSTM, BiGRU, and CNN with BiGRUs. So we have reason to select these algorithms or models to appropriately sequence-based tasks in code switch detections. So the model has shown particularly effective, their unique and strict handling spatial data. Then page 12. Hello. So this is the proposed system with CNN algorithms. As far as this, the hypothesis is, for example, the Ethiopia political radiation is slow. From here, there is code switch. Then these texts, they must be pre-processing. After pre-processing, there must be this assigned more political phase. That means this, then which means reduction is code switch. That means the intra. So after this, there is the language or code switch reduction. They must be assigned is more political. This adjective, noun, verb, or adverb. Then after that, they must be passed to word embedding, that embedding layers to vector representation. Then after this word embedding, there must be passed for CNN, that means future extraction. And after future extraction, then there must be classification or detection phase. There must be the sentence is non-code switch or intra-code switch or tag code switch or intra-sentential code switch. So page 30. So we have used those parameters. Those parameters. Then next page. Page 40. Next page. Hello?
Slide 14, please.
So for this research work, dataset was collected from social media such as Facebook and Twitter comments and posts. So the collection process yields appropriately 7,341 sentence features, which code switch and as well as non-code switch text. So for class, we have used 7,341 sentence, both code switch and non-code switch. Next page. So we have prepared data sets similar like this. There is the Amharic-English code switch text. The text is non-code switch as well as code switch. That means mixing of English and Amharic. And the other one is levels or detection code switch classes. Then non-code switch intra. That means we have level is 4 classes. So next page. Page 16.
It's on page 16, you can proceed.
So the performance evaluation and testing, this research work was compared with 3 the individual algorithms and 1 hybrid algorithms. CNN, PLSTM, BiGRU, and the hybrid of CNN with BiGRU model. So the paper was splitting data set, 75% for training. Among here, we have used is 15% for validation and 25% for testing. So we have used training testing mechanism. So in conventional neural network, this research paper was the parameters was conducted. Then epoch is 100, batch size is 64. Then optimizers we have used Adam, and learning rate we have used 0.001, and the other one is regression techniques. So for preventing overhandling and overfitting and underfitting, we have used over dropouts. That means we have used 0.6. As performance show, training accuracy was around 99.3 we have achieved, and validation accuracy we have achieved is 95% 4%. And also the last ones we have achieved is testing accuracy approximately 95.95.8%. So the paper has selected parameter after try each experiments. Page 17. Page 17. So this is our conclusion matrix. Page 18. Next page. Next page. Okay. So we have achieved this when we do this research, then evaluating is precision, recall, and F1 score. Then with 4 class. So based on this, we have achieved this. We have achieved this 95.8 testing accuracy. So first we will discussion part. Page 90. Page 90. So we conducted our research using corpus 7,341 sentence, with including course-usage and non-course-usage instance. So we have used comparative analysis was conducted involving various deep learning algorithms, which means deep learning with bijaribs. So when you use this CNN, we have achieved training accuracy is 99.3%, and we have achieved is testing accuracy 95.8%, and we have also is achieved is F1 score 95.6. And when you have used this BioLSTM training, we have both training case, training accuracy 955, and testing is 9 and F1 score 9 to 92.9. And when you use this by JARU, we have got 95.6% for training accuracy and 93.68 for testing accuracy, and we have got also 93.4% for F1 score achieved. And when you conducted with this the combination of CNN with BioJaru, we have got training accuracy 97.6 and testing accuracy 93.8, and F1 score we have got 93.7 accuracy. Based on our experiment data results, the studies conducted the conventional neural network slightly outperform 3 deep learning algorithms and 1 combination or hybrid algorithms. Next page. So when comparative analysis of deep learning algorithms with dataset ratio,
Karmao,
we have, well, yes.
You have used all your time. Please finalize in 1 or 2 minutes.
Okay. So we have also done with trial experiment with dataset ratio. That means dataset ratio is 80 by 20, 75 by 20, 25, and 70 with 30%. So based on this, we have got best result is this data ratio is 75 by 25%. And also we have got is the training loss, validation loss, and testing loss, these results. Okay. Next page, next. Conclusion part.
Can you tell us the slide number?
Yeah. So the main goal of this research course, getting deep learning algorithms, automatical Amharic-English course detection. Then the research is multi-processing module and then architecture modules. Under this pre-processing module, we have done is tokenizing, English morphological post-tagging, normalization, and then removing unknown word or nonsense words. And also we have when the other ones is architecture is involving word embedding with deep learning modules. So for pursuit detection of this CNN with Bajario, so ultimately performance deep learning algorithms we have evaluated with confusion matrix spaces. So we have selected these CNN names based on these our experiments. So the research work is performed 99.3% training accuracy and 95.8 testing accuracy and 95.6 for F1 score. So the English part. Next page. Next page. Hello. Next page. The other ones we have recommended this paper. So this research paper has English syntax cursive detection feature, extraction of this word. Hence, the paper is recommended with English semantic for Amharic-English cursive should be done. The other ones, the paper is considered with only Amharic-English cursive. So when Latin and semantic script, so the paper is suggested should be done the same script when Amharic-English is used semantic script. And the other recommendation is the paper was conducted text-based. So the paper was recommended with done speech cursive detection with whether audio or video. And the last one is we recommend to the paper is done the cursive. Okay, thank you for your attention. Thanks.
Okay, thank you. So I will start with a simple question so that I understand your work. In Amharic and English code switching, in the examples that you showed and in your document, we are using two distinct scripts. And it seems to me if we are using two distinct scripts, it would be a straightforward identification. So, I mean, what does your methodology add than just identifying the script from the Unicode itself?
Okay, shall I address?
Yes, you can address.
Okay, thank you your raised questions. So this paper is focused on this Amharic and code switch. That means the Amharic is written in standard text, which means Semitic script, and the other code switch is English, when written is Latin script. So we have focused on this, but we have not considered with when it comes to this the same script. That means both English and Amharic is written with the Semitic script. So we have not considered on this paper. So the methodologies we have used data science, the data science design. So we have to design, we have to develop, and we have to evaluating an artifact. So the methodology is data science, and approach is
if I may interrupt you, Gurmo. So it's correct that your data for the Amharic you are using the Semitic script, for the English you are using the Latin script, yes?
Yeah.
Wouldn't wouldn't it be better if you use maybe the Latin script for both or the Semitic script for both? Of course, it's Admittedly, many people do not use the Semitic script for English, but some people use the Latin script for Amharic. And in that case, there would be a real problem to address. In my opinion, since we are using two distinct scripts, there is no real problem that needs to be addressed, but you may take this as a comment, and if there is some misunderstanding, maybe the audience can also reflect. Thank you.
Okay, thank you.
Okay, so a question from the audience.
Can you hear me? Yeah, okay. I think you are, as Dr. Bisrat also raised, I think you are doing just classification. So maybe we can write a simple algorithm or code that can detect the English alphabet, maybe Latin alphabet, and from the Ethiopic alphabet. So what's your real contribution in that? Then you have classified into, I think, 4 classes. Then what's the next step? So what's the advantage of knowing which type of code switching is there? Is there any advantage after that, after the output of your research? These are my 2 questions. Thank you.
Girma, you may reflect.
Okay. Thank you for best questions. So, as I told you in significance of this paper, the main significance of this paper is reducing its Amharic language NLP tasks, such like hate speech, or machine translation, or sentiment analysis. So the main purpose of this paper to reducing this challenge, as well as to preventing language. The main state of art of this, first of all, there is a data set here, pre-processing, then removing unwanted data or nonsense word data. There must be word embedding, then pass to deep learning algorithms. Then after that, the module is then detected. The sentence have code switch or not. Then when the sentence is non-standard, that means then there is code switch. What type of code switch? These are code switch or intra or intra-sentential, which means the word level or phrase levels or sentence levels. So it used to predicting localization of words. That means translate to standard sentence. So ይህን የፈለግነው ምንድን ነው? እንደ ክላሲፊኬሽን አድርገን የተሻለ ሁለቱንም ሞክረነዋል። ነገር ግን በክላሲፊኬሽን ወስደው ፋይናሊ የዚህ ፔፐር ምን መደረግ አለበት? ወደ ስታንዳርድ ቴክስት መቀየር አለበት። ወደ ስታንዳርድ ቴክስት መቀየር አለበት። ይህን ስታንዳርድ ቴክስት ደግሞ ስንቀይረው በምን ሌቭል ነው? ወርድ ሌቭል ፍሬዝ ነው ወይስ ደግሞ ይህን ክላሲፊኬሽን ፋይናሊ ይሄ ምንድን ነው? እነዚያን አድሬስ ልናደርጋቸው ያ ማለት የሄድ ስፒችን ቻሌንጆችን አድሬስ ለማድረግ there must be convert standard text. Have you satisfied?
Thank you for the presentation, Girmao. I'm sure the audience will contact you since we have your contact information regarding further questions. Thank you very much. So now we have one final paper for this afternoon's session, which is automatic Amharic Tigrinya translation using statistical machine translation approach by ገብረእግዚአብሔር ገብረሊባኖስ and Tasfa again from Adigrat University and Bahar Dar University. ገብረእግዚአብሔር ገብረሊባኖስ will present via Zoom. But before we directly go to this presentation, I would like to remind you that tomorrow morning we will have similar session for the natural language processing. So tomorrow morning, I would like to invite you all to attend similar presentations, which will be then finalized by the closing remarks and the closing session in the main hall around noon. So this is a reminder for tomorrow's session. Now we can go to a presentation on the final one, automatic Amharic Tigrinya translation using statistical machine translation approach. Thank you.
Hello. Thank you. Let me introduce myself. My name is Gabriel, and I will present on the title Automatic Amharic Tigrinya translation using statistical machine translation approach. Here is the outline to present: introduction, related work, background of statistical machine translation, designing methodology, experimenting result, conclusion, and teacher work. Let's start with the introduction. The globalization and rapid development of the internet increase the interest of exchanging information among different groups. The information is available online on various languages. In addition to that, the human capacity to know this language is limited. Then, to know or to understand this thing is translation to their language is necessary. When considering in our case study, we are translating from Amharic into Tigrinya. Then Amharic is the second most Semitic spoken language after Arabic, and it is also both of the language are also the working language of the country. And Tigrinya that is spoken in the northern part of Ethiopia and Tigray region, as well as in Eritrea. To incorporate this this translation is it is difficult using a human translator to since the human translator doesn't get in every time and in every place. Then machine translation have a great role to solve these things. This study explores the following research question: can we achieve general understanding of translation among these things? Which unit, whether the word or the morpho based is better, and can the machine learning algorithm apply for this morphologically rich languages? The next thing is the related workers. What are the things that have worked on these languages? Then we have two close related workers among the Amharic and Tigrinya translation. For on Amharic and Tigrinya, on that part it uses around 13.49 as a plus score. When we consider about the background of the statistical machine translation, the machine translation is a field that is used to translate from one natural source language into another target language using a computer software without a human translator. To implement these things, so we have two mechanisms. The first one is using the rule-based. The next one is using the corpus-based. The rule-based one is controlled using some linguistic rules. Everything is controlled by rule, whereas the corpus-based is we need to prepare huge amount of data. Depending on this data, the system itself can learn on this parallel corpuses. Then our work uses the corpus-based since Amharic-English and morphologically Amharic languages. Generating every rule for these languages will be very difficult, but learning the system depending on the data will be the preferable one. Here it shows the how we can translate from the source language Amharic into Tigrinya, and mathematically or in occasion we can get the probability of Tigrinya given that a source language of Amharic, and we get this part, probability of Amharic given that Tigrinya times probability of Tigrinya, and this indicates the first one. This indicates for the translation method, whereas this probability of Tigrinya given the probability of Tigrinya is indicating for the language model. Here is the general architecture of our work. In our work, we need to collect two corpuses. The first corpus is the bilingual corpus, a corpus that needs among these two languages, Amharic and Tigrinya, as well as the second corpus is for the target language, the monolingual corpus. This monolingual corpus deals only for the target language. After we collect the bidirectional, the bilingual as well as the monolingual corpus, the next step is the pre-processing steps. The pre-processing step, we perform tokenization, cleaning, and we have a second experiment that performs using unsupervised segmentation, and we perform unsupervised segmentation for the second experiment. Having a pre-processed data set for the bilingual as well as for the monolingual part, we need to generate the language model as well as the translation model. The translation model is generated using the Giza++ tool, and the language model is generated with the help of the SR-LM language model. After generating these two things, the translation model as well as the language model, we need to generate our knowledge or our model here. And our model is generating the Moses decoder. At the end, we need to insert Amharic values into the model, and it generates the most probable equivalent Tigrinya for the inserted input value. Here, let's see the role of the translation model and the language model. The role of the translation model is to align words and phrases from the Amharic into the Tigrinya. It doesn't consider the grammatical order on this translation model. And the role of the language model is to generate or to create a fluent on the target language, or a grammatical correctness on the target language Tigrinya, and it uses in-gram calculation to perform these things. The next thing is the decoder. The decoder is the role of the decoder is to find a best translation, and we implement this decoder in this Moses toolkit. And the unsupervised segmentation part, or unsupervised morphological segmentation, we implement using a Morpheus its role is to generate a morpheme, or we need to break the word into their into their morpheme basic. The next one is the validation and tuning. The role of the validation and tuning will be when we are increasing our data set, its translation quality will be increased too, but its computational process will be increased. Since our data set will be increased, its processing capacity or its logic capacity will be increased. Then how can we optimize these things? And then the translation can be optimized using the validation part, and this one shows our blue score result. Let's see how we can collect our data and pre-process our data. Our data, most of our data is collected online from the OPS, and the data can be organized in the bilingual as well as on the monolingual part. The bilingual part consists the Amharic as well as the Tigrinya, and our data is stored in Notepad. Then Amharic.am.txt and ti.txt indicates for the bilingual, and lam.txt indicates for the monolingual part. After we collect our data, the next step is pre-processing, and we perform pre-processing using a Python script. And the next thing is the tokenization. The role of the tokenization is to reduce the data sparseness, and in this part, the tokenization part is used to separate words from punctuations. In our data, mostly we use some punctuations, arat point, arat native, some hyphens, and some things. Then we need to separate the words from these punctuations. The next thing is the data cleaning part. This data cleaning part is performed only for the bilingual purpose, and this data cleaning needs to remove very long sentences. If we have above 80 words in one sentence, it needs to remove from both source and target languages. And if there is empty sentences or empty line in our file, it needs to remove. In addition to that, if there is a misalignment between the source as well as the target language, it needs to remove. Here we will see the experiment. In order to, we have to experiment this. The first experiment is performed for the baseline. And in order to perform this experiment, we need to take the pre-processed data for both bilingual as well as for the monolingual data. Totally, the bilingual data is around 200,000. And this 200,000 data sets must be separated into training, development or tuning, and testing using a Python script randomly. And it is training, it is separated ratio is 80% for training, 10% for development, and 10% for testing part. And our language model is used X3 language model for around 1.5 million sentences and phrases in the target language Tigrinya. Here, let's see how we can test our system. The testing mechanism for the model is using the separated test dataset. The separated test dataset consists of test Amharic.txt and test ti.txt. And then for this one is for the Amharic and this one is for the Tigrinya. Since our role is to translate from Amharic into Tigrinya, this test.amharic must be converted using the module created, and its result must be stored in this test.txt, and this test.txt must be compared with the original separated data set, that is test underscore TI for the Tigrinya. Comparing these things, we get around 22.28 blue score for the baseline. The next experiment is performed using the unsupervised segmentation for the proper data set. Then, by taking a supervised segmentation, we get a better result, 25.28 blue score when we are comparing with the baseline. Here is the comparison between the baseline and the unsupervised segmentation. As a conclusion, this research work demonstrates the viability of translating between Amharic and Tigrinya using both baseline as well as the unsupervised segmentation. This study incorporates using 200,000 parallel corpuses and around 1.5 million for the multilingual corpuses. And the score of this experiment, the bottom score of this experiment is 25.28 using the unsupervised segmentation. And as a conclusion for the raised research questions, even if we get a better translation comparing the previous related workers, it is not fully understandable since our result indicates 25.28 as a better result, and it is below 30, then it is not fully understandable. The next one is the morpheme-based translation is better for this morphological language, since we get around 3 when are comparing between the baseline as well as the unsupervised segmentation, and machine translation can apply for this morphological rich language, Amharic and Tigrinya. As a future workers, the first future work will be the data enrichment by encouraging the data sets in order to test its results to achieve the fully understandable. And the next recommendation of future work will be we get a better result when we are using unsupervised segmentation. Then it is better to check using a supervised segmentation, especially using the conditional random field and the HHM modules. And the last recommendation will be using a speech-based machine translation, since our system is incorporated only for the literature part, and incorporated speech-based will be a future work. Thank you.
Thank you. I think the online Zoom session is not working at the moment. Anyways, thank you all for attending the entire session. I would like to appreciate your attendance. I would also like to appreciate the attendance of the presenters. We apologize for some of the delays that was present due to connection issues. But anyways, we have successfully completed today's session on natural language processing. So I would like to thank the technical support staff that we have here with us for the successful completion of the online presentation by the presenters. Okay, so we have the last present an opportunity for question and answers, but let me finalize. So anyways, thank you the technical staff at the back for your dedication and support in completing this session. Gabriel Xavier, are you with us?
Yes, I am.
Okay, thank you. We had some disconnection, so that's why. Now I have one question. I mean, usually statistical approaches in language processing have issues with out of vocabulary words, and especially when you consider morphologically rich languages such as Amharic and English, we have such issue. And I missed in your presentation as well as in the document the methodologies that you have employed to deal with the issue of out of vocabulary. Can you please elaborate on this?
Okay, thank you. Yes, there are some out of vocabulary problems since our data says it doesn't incorporate everything. Maybe I didn't include on the presentation, but it is available on the document. There are some out of vocabulary when we use especially the baseline at the unsupervised part. It reduces this problem, but in the baseline there were some out of vocabulary things. And we recommend to increase the data sets since to get better translation. Its score is around 25.28, but in order to get generally understandable translation, its blue score must be greater than 30, and the problem is depend on that thing.
Okay, thank you. Any question from the audience? You can use the mic in front of you, just push the button that's yours, yes.
Thank you, Gabriel Xavier, for your presentation. I just ask one question. As you may read, there are a lot of papers in machine translation, and they use transformer architectures and achieving a good result. So I was wondering why you choose statistical machine translation.
Gabriel Xavier, you may respond.
Okay, even if there are the transformer based, but we need to try using the statistical machine translation. And even if I didn't come here with this transformer based, but until now I didn't get the transformer based workers, and I need to check whether to get a better translation by increasing the data set on the previous two workers, but I didn't check using this transformer based part.
Thank you. I do have two questions. The first is, I think your result is lower than the one which you stated on your presentation as reference. Why? This is the first question. The second question is, I think there is a work which is done on machine translation for Amharic Tigrinya using RNN variant and transformer. Are you review it before doing your research? Are you checked that paper and recompare your result with that paper, your statistical machine approach result, and the one which is already published. I think the paper is done in St. Mary University. Thank you.
Okay, thank you. For the first question, our result is better than the previous two works. The first better result for the 7 CTPN pair language is 21.49, and when we're comparing with our result, it is better since we get 25.28. Then we get a better result comparing the previous two workers. But for the second question, I didn't get that paper. Maybe it will be depend on my searching part, but I didn't get that result. It depend on the Amharic and the Tigrinya part. Maybe there are another workers that are done using the that method, but I didn't get that work.
Okay, thank you for the presentation and for the question and answers. Again, I would like to thank all the audience that participated in this session. Tomorrow morning, we'll continue with our session. Thank you. Have a good night.
Thank you. Good.